You have to plug an electrical guitar into an amplifier if you want it to be more than barely audible. A guitar amplifier is typically a boxed unit containing an amp to boost the electronic signal and a loudspeaker. Some amplifiers use state-of-the-art silicon chip circuitry, while others use traditional vacuum tubes. The amp's electronics are housed inside a metal chassis. This model's chassis is made from a sheet of metal that's less than 0.04 inches thick. A computer-guided machine called a turret punch cuts the contour and pierces a series of holes and slots for the controls. A worker then uses a computer-guided bender to shape the chassis cutout. Elsewhere in the factory, the amp circuit board takes shape. It'll go inside the chassis. A computer-guided drill makes tiny holes in a laminate board that's coated with copper. The holes are for the board's various electronic components. An automated silkscreen printer now applies a diagram of the electrical circuitry in ammonia-resistant ink. Then the board goes into a machine called an etcher, which uses ammonia to dissolve the copper coating. Copper shielded by the ink diagram stays intact. The machine then rinses the board with sodium hydroxide to dissolve the ink, leaving behind just the circuitry diagram in copper. This copper configuration will conduct electricity to the circuit board components. Automated machines insert the smaller components. Here's what that looks like in slow motion and at actual speed. As a worker provides counterpressure, a machine folds over the leads of some larger components to secure them to the board until they're soldered. Workers then install large irregular parts by hand. Among them, the sockets that hold the tubes which power the amp. The ribbon connectors that join different areas of the circuit board, and the wires that connect external components to the board. The factory permanently affixes everything in one shot, using a process called wave soldering. The circuit board runs through a bath of molten tin and lead. In just a couple of seconds, the liquefied metal hardens, bonding the components securely. Back to that steel chassis we saw them bend into shape earlier. Since then, they've painted it black. With a silkscreen printer, they apply the control markings, logos, and other information. They begin the final assembly. First, they screw the circuit board into the chassis. Then they plug the preamp tube into the appropriate socket on the board. This tube boosts the electrical signal coming from the guitar and feeds it to the output tubes, which up the voltage level, making the signal stronger and louder. After installing control knobs and covering the bottom of the chassis, workers insert and clamp the output tubes, the number of which usually varies according to how many watts of power the amp is designed to produce. The chassis housing the electronics goes into a box. This factory builds its boxes from high-grade Baltic birch plywood, but other companies often use domestic plywood, MDF, or even plastic. After covering the box in leatherette and adding corner reinforcements, they install the two remaining components, the spring reverb and the speaker. As the guitar's electrical signals run through the amp, part of the electrical signal diverts to one end of the spring, vibrating it. The spring's other end picks up this vibration and sends it back through the amp as a delayed signal. That reverberation combines with the original signal to produce a bigger sound. We rip it open with barely a thought, more anxious to read its contents than to take a moment to truly appreciate its form and function. And then we ruthlessly discard it. The humble envelope just doesn't get much respect, despite its distinguished 4,000-year history. As early as 2000 BC, the Babylonians baked special clay wrappers to transport documents. Eventually, people made envelopes from lighter materials such as animal skins and leaves. By about 1000 AD, it became the custom to simply fold a letter and seal it with a drop of wax. But everything changed in 1837 with England's new penny postage system. To mail a letter, the sender now had to buy a postage-paid paper wrapper that folded into an envelope. One of the many envelope styles this factory makes is a 12 by 18-inch envelope made of natural color craft paper. A machine appropriately called the sheeter cuts the roll into 21 by 25-inch sheets. A worker selects the cutting die for this style and installs it on an automated press. As each stack of sheets passes underneath, the press applies 11 tons of pressure, forcing the die right through like a giant cookie cutter. The shaped sheets are called envelope blanks. Workers now load the blanks into the feeder of an automated piece of equipment called a blank sheet envelope folding machine. As we see here in slow motion, revolving steel blades first make score lines, 4 in all, one down each side creating the envelope side flaps, one across the top creating the seal flap, and one across the lower end creating the bottom flap. Folding blades hold the paper down along the score lines, while arms push up from underneath, folding the side flaps toward the center. Just before the flaps meet, the machine runs a line of glue down their edge. The flaps adhere to each other, forming the center seam that runs down the back of the envelope. The machine then glues the bottom flap and folds it closed. You can see in slow motion how it also applies glue to the seal flap at the top, keeping that flap open so that the glue will dry. The sender has to just re-moisten the glue to seal the envelope. The finished envelope exits the folding machine and enter another machine that counts them and stacks them upright. This more sophisticated piece of equipment is called a web roll envelope folding machine. They feed the roll of paper directly into the machine, and as we see here in slow motion, it does everything from cutting, scoring, folding, and gluing the blanks to counting the finished envelopes. For this style, a die even punches out an address window in the front of the envelope. This all-in-one machine goes through all the steps at lightning speed, 20 envelopes per second. The thin transparent film that covers the address window is usually made of polypropylene. The machine cuts it to size and glues it to the envelope. This machine doesn't have folding blades to hold the paper down along the score lines. Instead, the blanks roll through a series of rotating cylinders with air holes. A suction system vacuums the blank to the cylinder while the operation is being performed, then releases the vacuum to transfer the paper to the next cylinder, where it's vacuumed on for the duration of the next operation. Internal mail envelopes are opened and closed repeatedly, so they don't have a lick and stick seal flap like regular envelopes do. As we see here in slow motion, An automated machine rivets a cardboard button to the back of the envelope. At the same time, it rivets another button with a piece of string to the flap. Envelope factories use many different types of paper, from top-quality vellum to craft paper. With printing equipment incorporated right into the folding machines, they can print return addresses, even elaborate custom designs. Every day, millions of people around the world use escalators in places like shopping malls and airports. Escalators can move 100 or more people just as easily as one. Driven by a motor, these moving stairways make it very convenient for people to get around. Riding an escalator is easy, but building the smoothest and most quiet ride possible takes expertise. It starts with workers welding together the structural framework of the escalator. Like the chassis of a car, the track system and all other components will be bolted to this frame. A worker puts together the main drive gear, which hooks up to a motor with a chain. It will pull the steps and the handrails. He puts on an emergency brake device and uses bolts to secure it in place. He attaches side frames to the gear to make what is called the transition assembly. This assembly includes a drive gear for the handrail and allows the steps to loop back at both ends of the escalator. He then lowers the completed transition assembly into the truss, the hollow structure of the escalator. With the transition assembly in place, workers then install a cone plate, the last part of the escalator a person steps on before getting onto the moving steps. A worker makes the steps using aluminum ingots, which he puts into a crucible. They then apply a release agent to the mold used to make the steps. Spraying more lubricant on the mold ensures the aluminum stair will release properly from the die-cast machine, which automatically receives the exact amount of molten aluminum needed to make one step. A robot then takes the one-piece step from the die-cast machine and carries it to the trimming department. Here, a trim press removes some residual aluminum. The excess material goes back to the crucible to be recycled. Once the robot finishes a general trimming of the step, it sends it to the finishing department. There, finishing robots then file off the sharp edges. The robot also files in between the teeth that go across the step. Then it passes the step over a belt sander, making it smooth to the touch. Transformed from solid aluminum to a casting that is painted and assembled, the step is now ready to be installed. A worker rolls out a chain of rollers called a step chain. He greases all the pins. Then they place all the steps into position. Workers then connect the axles on the steps to the pins in the step chain, and then lock them together using a spring clip. They feed the required length of chain and steps into the unit. A worker then attaches a turnaround track. The turnaround track allows the length of steps to make a continuous loop from one end of the escalator to the other. The escalator runs for about 5 hours to ensure it operates quietly and properly. During this testing period, it goes through up to 250 quality control checks. After passing all the tests, workers wrap the unit in heat-shrink plastic. The escalator is now ready to load on a flatbed truck for delivery to the customer. Every time you talk on the phone or go on the internet, what you say or type travels to its destination through fiber optics. Voice and data gets transmitted via pulses of light through hair-thin glass fibers. Those fibers start out as large glass tubes. First, workers unwrap the tubes. Then they submerge them in a corrosive bath of hydrofluoric acid that removes any oil residues. Then they set a tube into each end of a lathe. As the tubes spin, they're heated with a hydrogen-oxygen flame. When the glass turns white, it's getting close to hitting peak temperature. At about 3,500 degrees, the two tubes fuse together. They put this new, longer tube onto another lathe. As the tube spins, they inject a mixture of chemical gases inside, while a traversing burner heats everything up. The gas mixture contains liquid forms of silicon, an abundant chemical element found in nature, and germanium, a chemical element similar to tin that's used as a semiconductor in transistors and other electronic devices. As the gases heat, they undergo a chemical reaction that leaves a white soot on the inside of the glass tube. The heat fuses the soot, forming what will eventually become the core of the optical fiber. The glass tube itself will form the fiber's covering. When there's enough fused soot, they turn up the heat until the soot itself turns into glass. Then they heat the glass tube enough to soften it, and to soften the new glass inside. The intense heat eventually makes the tube collapse on itself to form a solid rod. The internal structure of the optical fiber has been achieved. But it's in the form of a big bulky rod called a preform, so the next step is to thin it out. First, they excise the preform from the uncollapsed section of the glass tube. Then they install it vertically into the drawing tower, which will draw out the final shape. The drawing tower's oven heats one end of the preform to 3,600 degrees. The glass softens. Gravity helps pull it down, like honey dripping from a spoon. Then, using a glob of glass as a weight, they stretch the soft glass and keep stretching it until they formed a thin glass fiber. A series of pulleys measure the tension on the fiber as it's being drawn. A special monitor makes sure the fiber's precisely the right diameter, just 5/1000ths of an inch. Then the fiber passes through UV lamps that bake on an acrylic coating to protect against dust and other contaminants. Finally, the fiber is rolled onto a drum. From here, it's either shipped out as is or put into a cable. Fiber optic cables are expensive to produce. but they're smaller and lighter than traditional copper cables. They carry more information and need fewer repeaters to keep the signal from deteriorating. And unlike copper cables, they're immune to electromagnetic interference. They're also hard to tap without being detected. And all this is made possible by a complicated process based on a very simple principle: light traveling through glass. They're sleek, they're fast, and they're fun. Fiberglass boats can jump waves and turn on a dime. The fiberglass body is low maintenance and durable, so these watercraft don't deteriorate the way wooden boats can. A computerized saw cuts out the wood pieces they'll use to build the mold for the fiberglass boat. It takes a team of artisans about 15 months to design and build the mold. They first construct the frame. Then they construct the shape out of fiberglass. The mold must be perfect in order to cast a boat that's free of faults and defects. So they painstakingly work on the mold's finish, in particular, coating it in a special high-resistance paint that will withstand about 8 years of castings. Once they've finished the mold, they can begin casting the fiberglass boat. The equipment feeds just the right ratio of fiberglass to plastic resin. Fiberglass is glass in the form of very fine, flexible fibers. They may look fragile, but those fibers are stronger than steel. And they won't burn, stretch, or rot, so they make the perfect boat building material. Workers make sure they roll the fiberglass into every nook and cranny. This is critical, because if they don't apply the fiberglass thoroughly, the boat will have structural defects. As heat within the fiberglass builds up, it hardens. Next, they roll on a material called roving. It reinforces the fiberglass and makes it more rigid. They also install wood in the areas where they'll later mount equipment. They coat the wood with fiberglass to protect it from moisture. After about an hour, it's time to extract the casting from the mold. They use a lever system to lift out the hull. They cut out holes for the mechanics. Then they install the boat's deck. They install the motor and the electrical wiring for the mechanics and plumbing. The boat truly takes shape in the final assembly. They put together the upper part of the boat, called the shell, and the inside, called the liner. They install the furniture. Certain components are installed by hand, such as the dashboard. Last stop, quality control. A series of tests to ensure that all the mechanics function well and that the boat is absolutely watertight. Finally, a wrapping is added to protect the boat during shipping.